In this video, I'm going to demonstrate 4 observables. 4 things that you can verify yourself that demonstrate that the Gimbal UFO video almost certainly shows a glare that hides the actual object, and that the shape of the glare is only rotating because the camera is rotating. Briefly, the 4 observables are: 1. No rotation when banking. The shape does not rotate when the jet banks. Everything else rotates, the shape does not. 2. Bumps before rotation. When the shape does rotate, there's a bump right at the start, sometimes a fraction of a second before. 3. Rotating patterns. When the shape rotates, there's a matching rotation of light patterns across the entire image. 4. Derotation matches. The rotation of the shape matches exactly the amount of derotation needed for tracking the target. The first 3 are simple observations. They don't need any math to see their implications, just an understanding of the camera system. The last one does require math, but I can also demonstrate it with a simulation so you can see the math matches the physical reality. Before we get into the 4 observables, we need to understand what is going on. What are we looking at, and how was it filmed? The Gimbal UFO video is the poster child of modern UFO videos. It is the most interesting of the 3 videos taken by Navy pilots. It appears to show a saucer-shaped object skimming over the clouds. The object seems to slow down and turn on its end in a way that appears to defy aerodynamics. It's the only Navy video that seems to show good evidence of advanced technology, and so it's very important to people making the case that it's of extraterrestrial origin. Here I'm only going to make the case that what we are looking at is a rotating glare that hides the actual object. This does not mean it's not some really interesting object. That's still unknown, unidentified. I'm not going to address the audio that describes a fleet of them, or what's actually going on in the wider context of military planes in a training range. Just the rotating glare part of the puzzle. I'm also not going to address the location and the path of the object. That is, I believe, being answered by the work of Edward Current, who has built upon the analysis of various people to extract the flight information of the jet and to build a variety of 3D models that replicate the video. It turns out several solutions fit, but the simplest was found by modeling another jet about 30 miles away, flying away and a bit to the left. I'll include links to his videos and the discussion thread in the description. Before we get to the 4 observables, no banking rotation, bumps, rotating patterns, and the derotation match, we need to understand the camera, which in this case is an Atlia system on a US Navy FA-18. It's a targeting pod made by Raytheon. We're looking at an infrared image showing heat. The object in the middle shows up as hot. There's an aura around it that looks colder, but that's just an artifact of thermal imaging. What we are interested in is this saucer shape. We know they are zoomed in an incredible amount. It's in narrow mode with a 2 times additional zoom, so the camera is only showing about 1/3 of a degree of the sky. To put that into perspective, go out and look at the moon, which is 1/2 a degree across. Imagine a square about 2/3 that size. That's what the camera is looking at. So we know that when the pilot says it's rotating, he's just looking at the screen, the exact same thing we are looking at. It would be too small to see with a naked eye because it's several miles away. The camera is mounted on a 2-axis gimbal system. This might be a clue, as the official Navy title for the video is Gimbal, which might indicate that the gimbal system has something to do with it. Gimbal system just means that there are 2 or more rotation axes where rotating one axis changes the orientation of the other. With the Atlia camera, there's roll, where the front part of the pod rotates along an axis parallel to the bore sight, and pitch, where the ball at the front of the pod rotates around another axis. The roll rotation affects the pitch axis, so initially pitch is up and down, but if the pod rolled 90 degrees, then the pitch axis is now vertical, and pitch is actually left and right. To track a target, the pod uses a combination of pitch and roll to make the line of sight point at the target. Roll by itself will just move the line of sight in a circle, which is not that useful for tracking. Pitch by itself will move the line of sight along a line. This line sometimes coincides with a target, but usually you have to use both the pod roll and the pod pitch together. In the gimbal video, we are tracking a target that starts out at 54 degrees to the left of the jet and ends up 7 degrees to the right. This is largely because the jet is banked and turned to the left, bringing the target around in front of it. The movement relative to the clouds is parallax, and it slows down as we line up with the target, but does not stop, indicating the target has some movement to the left. What we are interested in here is the apparent rotation. The discussion and the simulation is all in terms of angles, which are all either shown on the screen or derived from data on the screen, and are independent of the actual distance to the object and its speed. As the object is tracked from 54 left to 7 right, it stays at a constant -2 degrees, i.e. 2 degrees below horizontal. In the simulator, this is shown with a white dot. Moving the target across the range of angles shows how the pod needs to modify its pitch and roll to track the target. The graph here shows the roll angle of the pod in a simple configuration with the jet horizontal. It starts out with a pod rolled about 90 degrees clockwise. Initially, most of the pod movement is pitch, but as the target gets closer to being straight ahead, the pod is forced to turn more, and there's a very rapid roll as it crosses straight ahead, and it ends up rolled about 70 degrees counterclockwise. It helps to see why if we turn on a view that shows the roll rings in red and the pitch lines in blue. Pitch can only go along a blue line, which is about all you need at the start. But towards the center, the pitch lines become perpendicular to where we want to go, so we have to rely on roll instead. The jet is actually banked to the left, which just changes the initial roll angle as it still has to roll the same amount, so the curve is the same, just shifted up. Now, if we look at the video, the bank angle of the plane, shown relative to the artificial horizon, is not constant. It changes bank angle to the left 4 times and to the right once. We can extract that data from the video with motion tracking and add it to the simulation. The banking to the left, counterclockwise, actually means that the pod needs to rotate counterclockwise less. This makes the curve a bit more irregular, but it keeps it in a narrower range at first. As well as banking, the jet has to pitch up a bit in flight to maintain an angle of attack. We use a base pitch of 3.6 degrees, which is in line with the values given in the FA-18 Ops Manual for 25,000 feet. This value is also scaled up by the bank angle to account for loss of lift. The interesting thing about pitching up the plane is that it flattens out the curve of the roll needed to track the target. The combination of banking and pitching reduces the required total roll by about 30 degrees. So now we've got a nice model of exactly how the pod should rotate and pitch to track a target from 54 left to 7 right, whilst correctly accounting for the motion of the jet. So what about this glare? A problem with rolling the camera, or in the case of the ATFLIR, what is known as the afocal four-optics, the front bit, is that it also rolls the image. For example, if we're looking to the left, then the camera is rotated clockwise, nearly 90 degrees. See the little triangle here in the view pyramid, or frustum, that indicates the top. The clockwise rotation of the camera means the image is rotated counterclockwise. Here's the pod's eye view. Compare it to what's in the box at the end of the view frustum. Now we don't want this rotation. We want the horizon in the display to look like the horizon out the window. So the ATFLIR includes an internal device called a DRO, short for derotation. That just takes the entire image and rotates it back to the correct angle. We see this explicitly in a video from other targeting pods. When you rotate an image that's the same size as the screen, then you get black regions, and you can see the rotating rectangle that's the original image. Notice here you don't see the black regions when zoomed in. Something else you see in this video is glare. Glare is light, or in this case thermal radiation, that spills out around a bright or hot object. This is often just a circular or oval shape, but can also have spikes in various directions. These spikes can be long or short, and the shape of the glare can be unrelated to the shape of the plane. In this video, there's a burning car, very hot, and a large diffraction spike. You see the spike rotate dramatically here, and at one point we see the message gimbal roll, pop up on screen before a major correction and glare rotation. Earlier in the video, we see the rotation of a smaller glare. It's not as dramatic, but it is rotating. Then we zoom out, letting us see the original frame before derotation. Notice that the glare rotates at the exact same speed as the original frame. This is because glare orientation is relative to the camera. Rotate the camera and the background will rotate, but the glare angle will remain unchanged. You can see this with glare in an iPhone. And look at the pod's eye view here with the glare added. The orientation of the glare does not change. So what eventually ends up on screen is the pod's eye view derotated. Since the dero derotates the entire image and the background has rotated, but the glare is fixed to the camera, then the end result is the background not rotating, but the glare is rotating. It's important to remember that dero isn't responsible for the glare rotating independently of the background. The dero affects the entire image the same. The separation of glare and background rotation has already happened. All the dero is doing is rotating the entire image to put the horizon in the right place. So now we've got a simulation of how a glare would behave with these angles. We can see it already looks fairly similar to the actual video, rotating the same amount and at about the same times. There are a couple of differences. In the simulation, with the early rolls of the jet, we see little rotations of the glare as the pod roll adjusts to the perfect angle. But in the real video, the target remains fixed in place for the first 20 seconds. And then, when the target makes its big rotations, they happen in steps in the real video, but in the simulation it's a smoother movement. To understand this, we need to understand the inner workings of the atflair. There's the two big external gimbals, the pitch and roll, but there are also one or two additional internal gimbals that can steer the line of sight with mirrors. These can be used to steer the line of sight without using roll. They are used to avoid gimbal lock near what is called the gimbal singularity, but could also be used for a variety of other situations. They are described in various patents from Raytheon. We don't know the exact configuration or how exactly they were programmed to operate at the time of this video, but we do know they are commonly used and they give the camera about 5 degrees of flex, where it can keep on target with the internal gimbals, even if the external gimbals are a bit off. I suspect what's going on is that it's trying to minimize use of roll to prevent loss of target lock, as well as optimally positioning the system for likely future movements. This is discussed a bit in the patents, saying that the roll axis may require significant power and is not fast or agile and may not be particularly accurate. So using the roll axis only for short periods of time makes sense if there's another system that can take up the slack more accurately. How much slack is needed? Well, we can take the angle of the glare in the video, extracted with image processing techniques and denoise with keyframing. We can then use that in the simulation to directly control the roll angle of the pod. This is the green line in the graph and the green dot in the simulation. So now at last we can get to our 4 observables. First, no rotation while banking. The simplest explanation for why there is no rotation in the first 20 seconds is because the pod is avoiding using roll. If we look at the angular distance between the white dot, the target, and the green dot, the line of sight driven by the glare angle, then they stay very close, actually within 2.2 degrees over the first 20 seconds. With 5 degrees of flex from the internal gimbals, there's no need for the slight corrections we'd need with just the 2 external gimbals. However, if this actually was a real object 10 miles away, and this was its actual shape, then when the plane banks, the entire scene should rotate. So if this was a real saucer-shaped craft, then it should also rotate with the horizon. Instead, it's fixed for the first 20 seconds. While it's at a fixed angle, the horizon, both the artificial horizon and the real one indicated by the clouds and the dark band above them, rotates 12 degrees in 3 steps over those first 20 seconds. This is probably the most significant of the 4 observables. You can see it simply by looking at the first 20 seconds of the video. Scrub back and forth. See the horizon rotate, but the object does not. Either something 10 plus miles away is precisely mirroring the exact small changes in the bank angle of a random jet, or it's an artifact of the camera. The second observable is bumps before rotation. Whenever the target rotates, we see just before this a little bump of the entire scene. This can be seen in the original video, but it's clearer if we use OpenCV to calculate a velocity field for the video. We see the motion of the clouds shift up a bit with the bump before the rotation starts. This means that there's a camera motion just before the object's apparent rotation. So either the object is zapping the plane with energy from 10 miles away just before it decides to rotate, or it's an artifact of the camera. The third observable is rotating patterns. When the object, the glare, rotates, we also see patterns of light in the background of the image rotate. This is easier to see if you cover the glare. They move in sync with the glare's rotation even when the jet is not banking. This can really only be explained as an artifact of the camera. Finally, there's the incredible synchronicity between the calculated roll, the white line, and the roll that's simply the same as the angle of the glare, the green line. For the first 20 seconds they were within about 2 degrees, no need to adjust. But at about 23 seconds we get over 2.5 degrees away and there's a small roll to correct. This happens again at 26 seconds, and then at 28.5 seconds it happens again. But this time, before the correction ends, there's a roll of the jet in a clockwise direction, which means the pod needs to rotate more in the counterclockwise direction, so we get this long correction until the jet stops banking. Then there's one more correction like the others, and finally we end just before another correction would be needed. So if this isn't a glare, then we've got an object over 10 miles away, probably 30, that somehow rotates when the jet rotates, so it stays fixed in the camera's frame. It's an object that somehow bumps the camera before it rotates from 10 plus miles away. It's an object that somehow projects rotating light patterns that rotate with it. It's an object that rotates in a way that matches exactly the amount needed to stay within 3 degrees of a gimbal system tracking the target while minimizing roll, but just from this one plane at this pitch and this bank angle. Or it's a glare, rotating because of the gimbal system in a video titled Gimbal. This isn't fudging the numbers or mental gymnastics. This is an open source simulation that you can try yourself. It's at metabunk.org/gimbal. The data was all extracted from the Navy videos, and you can verify that. There's extensive discussion threads on Metabunk about all of this, where I discuss what I'm showing here, and you can see the process of discovery and figuring stuff out. This isn't just me. Lots of people have done similar work. The lack of rotation was brought up by a Twitter user called Reality Seeker and was probably noticed by others before that. The roll of aircraft pitch was raised by Metabunk user Marcus, who also extracted the glare angle and demonstrated the close match with expected roll. Other people have done similarly. There were also additional discussions I don't have time to get into, like how the relationship between the steering Q dot and the azimuth verifies the 3.6 degrees pitch angle. Many people have helped. Many people agree. I know this won't convince everyone, but I hope it will help people understand the rotating glare hypothesis and why it's such a good fit for the data. If you've made it all the way through this video and still have questions, then I'd be happy to discuss them. I'd also be happy to demonstrate all of this with the simulator over a Zoom meeting, live on YouTube if you'd like. Finally, I know there's a question about if Raytheon's patents describe usage of the internal gimbals in this matter to give the arbitrary flex. They don't exactly, but they don't preclude it. The hardware isn't an issue, it's just a different algorithm, and we don't know which highly classified algorithm was in use that day. I asked the patent holder about this, and he said he was only authorized to comment about what was in the public patents. But we do know that this shape looks and acts exactly like a glare, so that's probably what it is.